5.5 minutes are missing from the recorded history of Swissair Flight 111. The cockpit voice recorder and flight data recorder stopped together while the MD-11 was still airborne, descending over the Atlantic near Halifax. The crew was alive. The airplane was still transmitting a radar return, but the electrical paths feeding the recorders had been damaged by a fire moving above the cockpit ceiling. Investigators would eventually recover almost the entire aircraft by weight. They would reconstruct its forward section from thousands of fragments and trace heat, soot, and melted wiring through spaces no passenger could see. Yet the part of the flight they most needed to hear ended before the aircraft did. The final sequence had to be rebuilt from radar, radio calls, electrical evidence, impact geometry, and the physical direction of fire damage. The missing interval also changed the standard of proof. Earlier actions could be matched to spoken words and recorded parameters. Later actions could only be inferred when independent evidence agreed. The investigation had to preserve that boundary because filling silence with a plausible sequence would make the story smoother while making the finding weaker. 53 minutes after leaving New York for Geneva, the pilots noticed an unusual odor in the cockpit. At first, the source appeared to be the air conditioning system. The odor faded. Then smoke became visible behind and above them. Within minutes, the crew sent an urgency call and turned toward Halifax, 56 nautical miles away. Nothing in that first moment displayed the size of the threat. There was no warning light for a fire above the cockpit. There was no detector in that hidden space and no extinguisher aimed into it. The first evidence available to the pilots was smell and a small amount of smoke, symptoms that could fit several faults with very different levels of danger. Airliner crews encounter odors from ventilation, electrical equipment, galleys, and cabin sources. Most do not mean that structure above the flight deck is already burning. The emergency therefore began with an information problem. The queue was real, but its location, fuel, and rate of growth were concealed. Above the pilots, bundles of electrical wire crossed metal structure and insulation blankets. Somewhere near the right rear wall of the cockpit, electrical arcing most likely provided the heat that ignited nearby material. The fire then developed in a concealed volume, beyond direct reach and largely beyond view, while the airplane continued through normal-looking air. This was not a fire that began as a bright flame in front of the crew. It was a technical sequence hidden behind liners, energized conductors, damaged insulation, a brief arc hot enough to attack nearby material, and combustible covering that could carry flame farther. Each stage changed the problem before the cockpit received a clear indication of what was happening. The fire did not need to burn through heavy structure to become catastrophic. It could follow light materials and wire routes, crossing from one equipment area to another. As heat weakened more insulation, additional circuits became exposed, increasing both smoke and the number of failures presented to the crew. At about 10:31 that night, the MD-11 struck the ocean roughly 5 nautical miles southwest of Peggy's Cove. All 229 people aboard were killed. The aircraft fragmented on impact and settled across a seabed about 55 meters deep. Local residents and rescue crews moved toward the site immediately, before anyone knew whether survivors could be found. The investigation that followed became one of the largest and most detailed in Canadian transportation history. Its purpose was not to create a simple villain. It was to understand how a modern long-range airliner could carry a growing fire through an area that certification checklists, materials standards, and recorder design had not treated as an immediately catastrophic space. The title of the official report states the sequence plainly: in-flight fire leading to collision with water. Behind that wording was a much harder question. Which protection should have prevented an arc from becoming a fire from spreading, and spreading fire from taking the systems needed to land? Swissair Flight 111 was a scheduled overnight service from John F. Kennedy Airport to Geneva. The aircraft registration HBIWF was a McDonnell Douglas the 1511, a wide-body trijet designed for long routes. 14 crew members and 215 passengers were aboard. The departure and climb gave no indication that the flight would become an emergency. The airplane carried the layers expected in a transport aircraft: flight controls, navigation, communications, cabin services, entertainment equipment, insulation, and electrical distribution. Those systems were installed for different purposes and certified through different assumptions. Above the cockpit, their wires and materials shared a confined physical space, so a failure in one layer could expose the others. HBIWF had entered service in 1991 and had accumulated tens of thousands of flight hours. Nothing about its departure identified an aircraft at the edge of structural life. The relevant vulnerability lay in ordinary installed materials and wiring arrangements that existed in related forms across other transport aircraft. After departure, Flight 111 climbed northeast along the Atlantic coast and leveled at 33,000 feet. The pilots communicated normally with air traffic control. The weather and airplane presented no immediate operational problem. For almost an hour, the flight looked like the thousands of ocean crossings that made Swissair's reputation for precision possible. That ordinary period matters because the accident did not begin with a damaged aircraft struggling from the runway. It began inside a functioning airplane after cruise was established. The available altitude offered time and range, but it also placed the crew far from a runway when the first ambiguous cue appeared. Cruise also changes the geometry of a diversion. Descending from 33,000 feet requires distance. A heavy aircraft must lose energy while controllers clear traffic and the crew prepares an approach. Those normal requirements become dangerous only when an unseen process imposes a much shorter deadline. The first officer noticed an abnormal smell and drew the captain's attention to it. They looked behind and above the cockpit seats. What they initially perceived did not remain clearly visible, and they discussed the air conditioning system as the likely source. That interpretation was reasonable from the evidence they had, but it framed the first response around smoke removal rather than a confirmed hidden fire. In aviation, procedures depend on classification. A visible engine fire, a cargo warning, and an unexplained cockpit odor do not begin from the same checklist. The crew had to turn a sensory clue into a system diagnosis while continuing to fly, communicate, and choose a diversion. The actual fire was developing faster than the evidence available to classify it. The cockpit ventilation system could carry smoke from a source that was not directly behind a visible panel. Looking toward the apparent origin did not reveal the fire's full location. The crew's senses described where smoke entered their space, not necessarily where combustion had begun. When smoke became visible, the crew transmitted PAN-PAN, the international urgency signal, and advised the controller that there was smoke in the cockpit. Halifax was offered as the nearest suitable airport. The aircraft was 56 nautical miles southwest of it. The crew accepted and received a direct clearance. A diversion is not one decision, but a sequence. Point the airplane toward the airport, descend from cruise, configure the navigation system, evaluate weather and runway, prepare the cabin, manage fuel and weight, and work the abnormal checklist. Every action consumes attention. Every mile flown also gives a concealed fire more time to damage systems. Controllers responded to the information they received and treated the flight as the crew described it. They shortened the route, supplied airport data, and coordinated the arrival. The danger was not a lack of available assistance, it was that nobody outside or inside the aircraft could measure the fire's development. The area above an airliner cockpit is not empty. It contains electrical cables, ventilation paths, structural members, brackets, insulation blankets, and equipment connections. Liners hide that complexity from the crew. In normal operation, the enclosure protects systems and finishes the occupied space. During a fire, the same enclosure can hide flame, trap heat, and delay recognition. Certification rules had concentrated detection and suppression requirements in areas already treated as fire zones, such as engines and cargo compartments. The overhead space was not equipped as one. The design assumption was that installed materials and wiring would resist ignition and that a serious fire would not propagate there unchecked. Critical systems cross this space because routing above a cockpit is normal engineering, not an obvious defect. Safety depends on separation, insulation, protection, and material behavior. When several assumptions failed together, physical proximity turned otherwise separate installations into one shared hazard. Electrical arcing occurs when current jumps across a gap or damaged insulation to another conductor or grounded structure. The event can be brief, yet its temperature is high enough to melt metal and attack nearby material. A protective circuit breaker may trip when current exceeds its threshold, but some arcs do not draw the sustained excess current needed for immediate interruption. That distinction is central. A breaker protects a circuit against defined electrical loads. It is not a universal fire detector. If an arc is intermittent, or if the current follows a path that remains below the breaker's operating threshold, damaging heat can appear before the cockpit receives an electrical warning. Arc tracking can also carbonize insulation and create a conductive path that grows across a surface. The result is not equivalent to a clean short circuit with a large immediate current. Protective devices designed around overcurrent may leave enough energy and time for nearby material to become involved. Investigators found several areas of arcing on recovered wires. One known arced cable supplied the in-flight entertainment network installed in the aircraft. That finding associated the entertainment system with the fire area, but it did not prove that this single cable created the first ignition. Fire damage can cause secondary arcs after a blaze has already begun. The official conclusion therefore stayed bounded. Electrical arcing most likely initiated the fire, and it most likely occurred near the right rear cockpit wall. The exact lead wire could not be determined. That is not a gap to fill with certainty. It is the line between physical evidence and a story the fragments cannot prove. Investigators examined routing, breaker history, metallurgical signatures, and the location of each recovered segment. Multiple candidates passed through the damaged region. Impact and fire had destroyed too much continuity to rank one beyond reasonable doubt, so the report separated the likely ignition process from the unidentified initiating conductor. Near the wiring were thermal-acoustic insulation blankets. Their covering included metallized polyethylene terephthalate, commonly shortened to MPET. The material had passed the certification test applied at the time. But in the aircraft environment, with seams, contamination, orientation, and nearby ignition energy, it could support flame propagation. A material can satisfy a narrow laboratory test and still behave differently when installed as part of a complete system. The question is not simply whether a flat sample burns. It is whether the installed material, its edges, fasteners, adjacent components, airflow, and ignition source allow a fire to travel through the actual aircraft. Metallization gave the blanket covering useful thermal properties and low weight, but it also changed how flame behaved at folds and seams. Investigators tested recovered and exemplar materials in configurations closer to service. Those results helped explain why fire damage extended beyond one small ignition point. Once ignited, the fire moved through available combustible material above the ceiling. Heat damaged wire insulation and generated more electrical faults. Smoke entered the cockpit through openings and airflow paths. Systems that had begun as independent layers became physically connected by the fire. This is how a hidden technical event becomes an aircraft-level emergency. The ignition does not have to disable everything at once. It only has to survive long enough to enlarge the damaged area. As insulation, connectors, and conductors fail, the crew receives more symptoms, but those symptoms arrive after the mechanism has already advanced. Smoke itself adds workload and reduces visibility. Crews may need masks and goggles while reading checklists, tuning radios, and monitoring instruments. The fire simultaneously creates failures and makes those failures harder to manage. What begins in an inaccessible volume changes the human environment below it. Air traffic control cleared Flight 111 toward Halifax and began arranging a descent. The pilots asked about weather and runway conditions. Halifax offered long runways and emergency support, but the MD-11 was still heavy with fuel for an Atlantic crossing. The crew discussed dumping fuel before landing. Fuel dumping was a normal tool for bringing a heavy long-range aircraft closer to its landing weight. In this case, it joined a growing workload whose true time limit was unknown. The decision has often been reduced to delay, but the record shows a crew managing an abnormal odor and smoke before the full scale of the hidden fire was apparent. Landing above the normal weight is possible under emergency authority, but it carries structural and handling considerations that crews must evaluate. Before the situation sharply deteriorated, the pilots were balancing a known heavy aircraft problem against a smoke source they still believed they could isolate. Martin de Tromler's first positioned the aircraft for Halifax. The crew indicated that they needed more track distance to descend and prepare. The airplane turned south over the water. This path kept the aircraft near the airport while creating room for descent and fuel dumping. On a map, the turn can look like a circle away from safety. In the cockpit, it was an attempt to convert a cruise aircraft into one ready to land. The decisive problem was that the fire's rate of growth was not visible on that map. Geography showed distance to the runway. It did not show the shrinking reliability of the aircraft. The flight remained within reach of Halifax throughout this maneuver. The unanswered counterfactual is not whether a runway existed, but whether any revised path would have beaten a fire whose exact growth rate and effects are known only in retrospect. The report did not claim a guaranteed successful alternative. The crew began the smoke checklist and changed electrical configurations intended to isolate cabin equipment and remove a possible source. Some cabin buses were de-energized. The checklist reflected an assumption that smoke from an air conditioning or electrical source would remain manageable long enough to identify and isolate it. Behind the ceiling, however, the fire was already independent of the original arc. Removing electrical power could stop an energized source, but it could not extinguish material that was burning. The procedure and the physical fire were now operating on different assumptions. Electrical failures began to appear across cockpit systems. Displays changed. Communications and navigation equipment were affected. The pilots declared an emergency and told the controller they had to land immediately. The language had changed from an urgency handled through preparation to a direct statement that time had run out. This was the moment the hidden fire became unmistakably operational. Yet the crew still had to fly an increasingly damaged aircraft at night over water, align with an airport they could no longer approach through a normal, stable sequence, and make decisions with instruments and radios becoming less dependable. At approximately 10,000 feet, both flight recorders stopped. Their common loss did not mark the impact. It marked fire-related damage to the electrical system supplying them. For the next 5.5 minutes, the airplane continued without the two devices designed to preserve its technical and human history. Radar still traced portions of the flight. Controllers heard the last radio transmissions. The wreckage preserved switch positions, heat patterns, arc marks, and failed conductors, but no source could replace the continuous recorders. The investigation would have to combine incomplete evidence and state its conclusions at the strength each fragment allowed. During that unrecorded interval, the aircraft descended and turned near the coast. Investigators could reconstruct broad movement, electrical progression, and the condition at impact. They could not reproduce every cockpit action or every spoken exchange. Claims about those minutes must therefore remain narrower than the evidence. The difference matters because a documentary can easily turn missing data into imagined drama. The official record supports a rapidly worsening fire, extensive system damage, loss of control, and impact with the ocean. It does not support invented dialogue or certainty about each decision after the recorders failed. The MD-11 struck the water at high speed and a steep attitude. The force fragmented the aircraft into millions of pieces. There were no survivors. The violence of that breakup might have made a technical investigation impossible. Instead, it determined the form the investigation would take: recover, sort, identify, and rebuild. Search and rescue became recovery. The exclusion zone protected evidence while ships, divers, sonar teams, military personnel, police, safety investigators, medical teams, and local residents worked around the clock. The sea was not only the accident site, it was the place from which the aircraft's hidden history had to be physically retrieved. The wreckage field covered an area roughly 70 meters by 30 meters on the seabed. Heavy lift operations recovered major pieces before winter weather could close in. Smaller material was gathered through repeated passes and careful screening. Ultimately, about 98% of the aircraft by weight was recovered. That figure describes an extraordinary mass of evidence, not an intact airplane. Each piece had to be cleaned, cataloged, and placed against drawings of the MD-11. Damage from the in-flight fire had to be separated from heat, deformation, and fragmentation created at impact. Recovery crews used sonar, remotely operated equipment, divers, dredging, and heavy lifts across changing weather. Thousands of people from Canadian agencies, the military, police, medical services, American organizations, and local communities contributed. The operation continued long after the immediate public emergency had passed. Investigators built a reconstruction frame and attached recovered portions of the forward fuselage in their original positions. The result was not a restored aircraft. It was a three-dimensional evidence map. Pseudorection, melting, discoloration, and missing material could be compared across the cockpit crown. Reconstruction converts scattered fragments back into relationships. A wire alone may show an arc. A blanket fragment may show heat. A structural piece may show soot. Placed together, they reveal where fire intensity increased, where airflow carried products of combustion, and which failures were likely earlier or later. More than 250 kilometers of recovered wire were examined. Investigators used magnification, electrical tests, metallurgical analysis, and three-dimensional location data to distinguish arc damage from heat and impact. Arc beads could show that current flowed at the moment conductors contacted, but sequence remained difficult when fire caused many secondary failures. The investigation was therefore less like finding one burned cable and more like solving a network. Which wires were energized? Which breakers opened? Which systems disappeared from the record? Where was each fragment installed? Which marks could only exist before impact? Every answer narrowed the fire's path without automatically identifying its first instant. Fire damage was concentrated above the cockpit, with the most severe area near the right rear wall. Evidence showed that flames spread across insulation and attacked wiring and equipment. The cockpit ceiling concealed this process until smoke and failures entered the occupied space below. That physical pattern supported a conclusion stronger than any single cable identification. The fire began above the cockpit. Electrical arcing most likely supplied the ignition energy. Combustible materials allowed propagation. The exact initiating lead remained unknown. The recovery also returned personal effects and human remains to families. Communities around St. Margaret's Bay had responded before the scale of the loss was understood, and many continued supporting the operation for months. Memorials at Bayswater and near Peggy's Cove face the water between them. An investigation can count fragments, catalog conductors, and reconstruct fire paths. It cannot reduce 229 lives to a system diagram. The technical work mattered because each conclusion carried an obligation: prevent another crew and another cabin from entering the same hidden sequence. The Transportation Safety Board concluded that aircraft certification standards for material flammability had not been sufficient to represent realistic ignition and installation conditions. Metallized MPET blanket cover material could propagate flame, and it existed across a large transport fleet. The response extended beyond this one aircraft. Authorities and manufacturers moved to remove or replace affected insulation materials. The lesson was not that every approved material was unsafe in every position. It was that a pass under an inadequate test could not guarantee acceptable behavior in a complex installed environment. The in-flight entertainment network also came under scrutiny. Its wiring carried power into the area where arcing was found, and aspects of its installation and protection did not provide the expected isolation. Swissair deactivated and later removed the system from its MD-11 fleet, and certification practices for non-essential systems received renewed attention. Non-essential does not mean physically separate. Equipment installed for passengers can share routes, structure, and power architecture with the wider aircraft. Certification must consider what happens when that equipment fails in the environment around it, not only whether its normal function interferes with flight systems. The report also challenged the assumption that crews would always have enough time to troubleshoot smoke before landing. Checklists commonly treated smoke as a problem to identify and isolate. Swissair 111 showed that a hidden fire could grow rapidly while its source remained uncertain. Later guidance placed greater emphasis on preparing to land without delay when smoke or fire cannot be positively controlled. This does not prove that one different turn would have saved Flight 111. It changes the system's default response to uncertainty. An unexplained in-flight fire is allowed to set the shortest practical clock. Recorder design became another safety question. Both recorders lost power from fire damage and stopped before the final minutes. The board called for independent power, longer recording duration, and ways to preserve information when the aircraft's normal electrical system fails. Recorders do not prevent an accident in progress. They protect the ability to learn afterward. When both depend on vulnerable paths through the same damaged region, one fire can erase the period when system behavior matters most. Detection and suppression in hidden areas received similar attention. Cargo compartments had defined systems because fire there was an acknowledged hazard. The space above the cockpit did not. The board recommended evaluating inaccessible areas where a fire could threaten safe flight and developing practical means to detect and control it. Detection changes time. Suppression changes growth. Neither is useful if the hazard is excluded from the design model. Swissair 111 expanded that model from named fire zones to any concealed region where wiring, combustible material, and critical systems can meet. The final report did not identify one person, one wire, or one decision as the entire cause. It described a sequence. Electrical arcing most likely began the fire. Flammable material allowed it to spread. Hidden placement delayed recognition. System damage accelerated. Procedures and certification assumptions did not match the rate of growth, and essential recorded information disappeared before impact. Each link was manageable only while treated separately. Together, they formed an emergency faster than the airplane's defenses could reveal or contain. That is why the investigation's uncertainty about the first conductor did not prevent broad safety action. The system-level mechanism was clear enough to change materials, wiring, checklists, and recorder standards. Near Peggy's Cove, the memorial looks over the same Atlantic water where recovery crews worked. Its names do not describe wiring, insulation, certification, or recorder power. They describe the people those systems were meant to protect. Swissair Flight 111 changed aviation because investigators refused two easy endings. They did not turn uncertainty into accusation, and they did not let uncertainty prevent action. They recovered the fragments, stated what the evidence could support, marked what it could not, and rebuilt the safety case around the fire that had remained hidden.